All right, so this lesson, bell. All right, one more time. So this lesson is our introduction to probability. We're going to stick with the real basic forms of experimental and theoretical probability, and then later on we'll get into conditional probability and then multiple events. But this is a real quick refresher on probability, and you've done probability questions like this for a few years now, so none of this should be quite a shock. So two types of probability we're going to discuss here: experimental versus theoretical. So experimental is what actually occurred in the experiment. So you collected data, you had a little tally chart, and you figured out what went on. So we're flipping a coin, let's see, 7, 3, so 10 times, 10 trials, we call it. And the probability that the coin landed on heads is 3 out of the 10 times. And of course you can write that as 0.3, that would be equivalent. I like fractions for probability, so whatever you want. But however, the theoretical probability that the coin should have landed on heads, if it was a fair coin, in theory it should land on heads 50% of the time. So out of your 10 trials, 5 out of 10, or 1/2 is how that would reduce, which is 0.5. So they're quite far apart, actually, the theoretical versus the experimental probability. So your next question as a scientist would be, well, what's wrong with my coin? And maybe that's not what's really going on. Maybe you only flipped the coin 10 times. It's not like you had a ton of trials. I have a feeling if you flipped that same coin, 10,000 times, you would get numbers that acted more like theoretical probability. So that's my claim. All right, this next part. Suppose the spinner was spun 60 times, so 60 trials, and it stopped on the number 4 14 times. What's the experimental probability that it will stop on 4? Well, that's asking what actually happened. So 14 out of 60 times, which does reduce to 7 over 30. I like reduced fractions for probability. And I don't think I covered this at the beginning of the lesson, but the definition of our probability is the number of successes over the total number of trials. There we go. What is the theoretical probability that it'll spin and land on a 4? So these are all equal segments of the spinner, and it looks like there's 5 equal segments, so 4 is one out of the 5 segments. It should have landed 20% of the time. Pretty close, not quite exact. For any spin, what's the theoretical probability it'll stop on a 3? Again, that is a 1 out of 5 probability. And then the next question is asking you to think like a scientist. So if the number 3 came up 42 out of 60 times, I mean, gosh, what decimal would that be? I don't know if I wrote down what decimal that is. Well, got it. Let's see. Cut by 6, so 7 out of the 10. 0.7. 70%. That's way higher than it should have been. It should have been 20%. So would you conclude that something's wrong with the mechanism? Probably. 60 trials is quite a bit of trials. So I think what happened, and I think we've all had this happen on our game board spinners, sometimes that spinner gets stuck. Like the board is warped in some way, so it keeps landing, or maybe the spinner mechanism itself is broken. So what would I conclude? I would conclude I have a faulty spinner. That was quite a lot of trials, and I don't think it's just by sheer chance that it showed up 70% of the time. So yeah, something's wrong with our spinner. We need to get a new one or fix it. The weather record for the first week of May for the last 10 years shows that it rained 14 out of the 70 days. So what's the experimental probability that it's going to rain? Well, that would be the 14 out of the 70. So again, you want to reduce when you can. This is, let's see, 2 out of 10, which is 1 out of 5. Keep reducing, huh? All right, the standard roulette wheel has slots 1 to 36, and then also a 0 and a double 0. So that's 38 different slots. And they're all the same size and all equally likely to be landed in. What's the theoretical probability it'll land at a number 7? So there's only one 7 on the roulette wheel out of the 38. So not a great chance. And you don't play roulette yet because you're too young, but that's the payout based on what your bet is going to be different. It's going to be different based on the probability of that event occurring. So like when you play roulette, you could say you're going to land on 7, or you could put your money on the fact that you're going to land on a black segment or a red segment. So all sorts of ideas. Don't ask me for advice when you're older because I have no idea how to play anything. All right, a poll of seniors showed that 110 favored Thu Pham for senior class president, and 100 favored Aurora Martinez, and 40 were undecided. So first you need the total number of people that were voting. So if we add those up, let's see, 240, 250. And then it says what's the experimental probability that someone chosen at random voted for Thu Pham. So that would be the 110 out of the 250, and I think I reduced that to 11 over 25. Again, decimal answers are okay, and when you go to college, I found that a lot of college professors and textbooks prefer the decimal answers because they can easily be converted to percentages, so it makes more sense, but I don't care. Alright, so here we have some experimental probability of a coin toss 20 times. Experimental of it landing on heads is 7 out of the 20. But theoretically, it should have happened half, right? Coin 50-50 chance of getting heads or tails. Which is not really that close. But again, we only had 20 trials, so I'm not ready to throw my coin in the garbage. I'm not thinking it's like a faulty coin or something. Alright, so here, I'm going to do some of this with you, and then the rest will probably be assigned. So they want you to compare experimental versus theoretical. So experimental, you don't see it here, unless it's coming up here, but there is a chart on our paper, and it has all the experimental data from our spinner. So like a 1, 2, 3, 4, 5, 6, 7, 8, and, oh man, drew right through my chart. There we go. And they tallied it up on our paper, so get my bifocals out here. Yeah, oh gosh, 4 times it landed on 1. How am I supposed to read this? 1, 2, 3, 4, 5. 7, 3, 8, 7, 9, and 7. And there were 50 total trials. Hope I read all those correctly. Alright, so experimental data is what's coming off this chart here. Theoretical is what should have happened. So experimentally, probability of it landing on 7, well, on 7 it landed 9 times, so 9 out of the 50 trials. But the theoretical probability of that happening would be 1 out of the 8 equal segments. Remember, there's 8 equal segments here. If you want a better comparison, we should put those as decimals, but I'm not going to bother doing that right now. Alright, how about the probability of it landing on 1 or 5? So a 1 or a 5 would be considered a success this time, so that would be 12 times out of 50, which of course reduces to 6 over 25. The probability of it landing on 1 or 5 for theoretical would be 2 out of the 8 segments, which is 1 out of 4. Alright, let's do this not prime business. Okay, not prime. So P.S. prime numbers, which everyone forgets. 1 is not a prime number. So 2 is a prime number, 3 is a prime number, 5 and 7 are all prime numbers. So not prime numbers would be 1, 4, 6, and 8. So not prime numbers for the, let's do theoretical, since I know that pretty easily off the top of my head. That's 4 out of the 8, which is 1/2. But the experimental probability of it being 1, 4, 6, or 8. 1, 4, 6, and 8. Let's see. 4, 7, 7, 21. 21 out of 50. Which I don't think that does reduce, so I'm going to leave it. Okay. I think I got them. Okay. This chart is just more of that. I'm probably going to select a few problems for you to do. Maybe we'll work in teams or something. I don't know. There's another worksheet where we cover just real basic probability. We're going to work together. Just remember, probability is it's always the number of successes out of the total number of trials. I prefer your probability written as a fraction. Of course, I'll take a decimal or a percent. We're going to get into more complicated probability next. Conditional probability, it's always a good time. And then multiple events as well.